Hello and welcome back to today's class. And this is a continuation of our Fourier transformation edition. And in our previous classes, we've discussed the importance of transforming a signal from time domain to frequency domain. But I will pause on that discussion a bit and we digress quickly to a part called frequency response. And we need to understand frequency response as it relates to transfer function, and it further relates to decibel power scaling and what are the tools like board plot that we use in making a graphical uh, plot of a transfer function in order to understand the behavior of output of a signal to input of a signal. So when we finish that part, we'll cite some examples as it relates to some uh, uh, filters, etc. After that, we'll go back to our Fourier transformation. But for the purpose of today's class, we're going to discuss uh, what we call frequency response. And you might have been wondering what is the meaning of frequency response, or if you are already in field of communication, you might have been hearing people discussing this issue a lot and this particular topic a lot, and you want to know more about it. So just by simple definition, what do we mean by frequency response? And what we mean by frequency response is that uh, frequency response is the uh, variation in the behavior of a systems as it relates to change in frequency of the input signal. Now, we say you have let's assume a system in our mind, just a black box system. We don't know what it contains. But now, we are now putting a signal from one part of the system as an input, and we are taking out output from the other side of the system. Now, we wanted to know, as we are putting that particular input signal, let's assume it's an input signal which is coming with a 50 hertz frequency, and we are taking out output. What will be the behavior of that output in relation to that 50 hertz frequency signal? Make a table and put the output, the result of the output, put it on one particular box in a table. Change that input again of that system. Increase the frequency. Let's say we decide to compress the frequency a bit more and we change it to 60 hertz, and we send that signal again into that system, into that black box system, and we take out the output again. There will be change, as it will be completely different from what we had when we had 50 hertz input signal. Put that also in another box on your table. Now let's even decide that we decided to compress even the signal more by changing it to 100 hertz, and then we send that signal as input signal as well into our into our black box system and take out the output. Now you can now see there are variations in the behavior of that systems as we are changing the frequency, and simply this is what we call frequency response. This is what we call frequency response. And we needed now to start to uh, now compare that when it was 50 hertz, this was what we got. When it was 60 hertz, this was what we got. When we change it to 100 hertz, this is the result. You can continue like that for maybe different uh, frequencies as well, and then you make a plot, and then you can see variations. And this is what we mean by frequency response. And different systems will respond differently to different frequencies, different signals as you change uh, uh, the frequency of that input signal. And this is why we are interested. We wanted to know how they are behaving. If it's just a signal that is just coming with a fundamental frequency and it has no harmonics, you can see it outside as well. What is the behavior? And if you have a fundamental frequency and it has other harmonics, when you send it also to that input, to that system, when you take the output, you will see it as well. Now, it is not clear how you can now relate your output to your input. But for us to do that, as you are talking about your frequency response. But for us to understand that, we needed something we call transfer function. And by transfer function, we mean the numerical, or let me say, ratio of between the output of a particular signal or a system to that of input. So you take the numeration to the numerator to the denominator of that system, what you get as output divided by the input, and then you can take the numerical value to understand actually what is actually happening in that system. Now, when you take transfer function could be in any way. It could be power ratio, it could be uh, input voltage to output voltage, it could be input current to output current. You take the ratio just to understand the what are the factor that is being played in that system. So, but that is that about transfer function. But when you now you only have numerical view of that system or the behavior of the system. You cannot have graphical view of that system. Now, you needed a tool called board plot before you can understand the graphical behavior of that system, so you can easily make plot of magnitude, phase, and then have a particular frequency on which roll all of them over, since you are changing your frequency as we say frequency response. Now before we discuss board plot, we needed a particular tool called power scaling, or let me say decibel scaling. Whenever you are discussing issue of power or measurement in frequency domain, we always talk about decibel. Why we're talking about decibel is just this is the unit we adopted, that is being adopted in terms of when you start to talk about frequency domain. So and this decibel scaling is always expressed in logarithmic mode. And you know that from log rule, we know that whenever we have a log of a particular log of A against log of B, let's say log A log B to base of 10, you know that when we want to express it, we are going to have log A plus log B, both of them in base of 10. The same way when we have log of A divided by log of B, in the case where we are taking that transfer function as output of a system to input of a system, to base of 10 as well. When we want to express it, we are going to have log A subtract minus log B base of 10. The same thing goes to a number in which we have, let's say, log of a number raised to particular power, let's say log A raised to power of x. When we want to express it, we are going to have x as a multiplying factor multiplied by a log A to that of base of 10. Also, we know that if you have log of a particular number which is raised to power of 0, let's say log A raised to power of 0, we are going to have any number raised to the power of 0 will become 1. And when you take log 1 to base 10, it's going to become 0 already. So that is that about that one. So, and that part, we'll stop there because we'll be using that tool when we now go to board plot. But now let's discuss board plot. So board plot, what we mean by board plot? Board plot is a semi-log plot of particular, let's say, particular transfer function, in terms of which is making you to be able to define your, or to plot your magnitude and phase against a particular series of frequencies. Let's say we already mentioned various frequencies before. We mentioned 50 Hz, 60 Hz, 100 Hz. You can roll that to even up to 1,000. And when you do that, you now have a graphical view in which you can have your magnitude and you can also have your phase. Now you have the possibility to understand the behavior of that system in terms of magnitude and also in terms of phase. And now that you have the possibility to do that, you can know at what frequency the magnitude is high and what is happening at that particular point in time, what is the phase as at that time. You can even determine your cutoff frequency if in case of filter design. If you are able to use this tool, we are going to take more time on this tool bring some more examples. We do graphical plot ourselves. Those of you who have been following the Saturday series, also in that particular class we are going to really do that one clearly so you can understand how to make that plot. But for the purpose of just this discussion, we have mentioned that is now with both plot, it's easy for you to now make that plot of magnitude, phase against frequency, and there you can see graphically what is the behavior of that system over that particular frequency as you are changing it. Now this is easy for a SISO system, that is when you have a single input to single output. In case of a MIMO system in which you have multiple input and multiple output, also this system you can actually separate them and have a plot as well. But it's not so easy like that, because then you have to do other things as well. So this is about both plot. Now we understand just briefly about both plot, but we now need to start to use this both plot. But for us to easily adopt this both plot, let's just say first we will not proceed. We needed to have system in our mind. An example of some systems are, let me say, filters, and we are going to work more on filters. In fact, we are going to even design filters ourselves, those analog filters. And one of them is, let's say you have a low pass filter in which you have a signal. Let's say you decide that I want a low pass filter in which from 0 to 50 hertz the signal should cut off. All the signals from 0 to 50 hertz should pass in that filter, and anything above 50 hertz should be cut off. That is one scenario which we call low pass filter. Another scenario is high pass filter, in which you design that let's assume that we are taking from 0 to 100 hertz, and you said all signals from 0 to 100 hertz should be cut off. They should not pass in that system. Just immediately after 100 hertz, those signals should pass in that filter, and that's the one we call high pass filter. So it's going and it's allowing all the high frequency signals to pass, and it's blocking all the low frequency signals to not to pass in that system. That's another example which we call high pass filter. Another example could be a band pass filter in which you said that, okay, let's say from 0 to 100 hertz all those signals should not pass in that system. You are only allowing just immediately after 100 hertz to 200 hertz. Those are the ones that should pass inside your filter, and immediately after 200 hertz all of them should be rejected. So you have a situation in which you have a signal in this way, which we call band pass filter. Another example could be that you have a band reject filter, which we call a band reject, in the sense that you are now allowing signals, let's say from 0 to 100 hertz, to pass on one particular side of your filter design. That's vestigial. And then you are now blocking, let's say from 100, just immediately after 100 up to, let's say 200 or 300, you are blocking those ones, and just immediately after 300 also you are also allowing your signal to pass either to infinity or to a particular defined value. So these are examples of filters, and we are going to discuss more about these filters as they are now related to transfer function, both plot and frequency response. And after that we'll return to our Fourier transformation, and when we go to Fourier transformation we will now see the importance why we have to discuss all these type of things that I've just mentioned in today's class. And that is it for today. Thank you for listening, and for those of you who are still interested in Saturday series, you can join us as well. We still continue that class, and try to share this video to your colleagues, those in universities and those who are interested, and also you can drop comment for me in case you have a question. Thank you for your time and have a good day. Bye.